In this lecture, let us discuss PCM systems. Okay, so that is system aspect. So let me now get into the system aspects of PCM systems, pulse code modulation systems. That is, a typical pulse code modulation system consists of the transmitter, channel, and the receiver. So the transmitter you are now quite familiar with, right? At the transmitter we have a message M of t, which must be low pass filtered. So you put a low pass filter with the cutoff frequency fc is equal to, let's say, 4 kilohertz. Okay, that means even though your message signal contains frequency component more than 4 kilohertz, but you are not interested in sending those frequencies. Okay, so therefore the low pass filter has to be there, because this is now immediately going to be followed by a sampling operation. Sampling, or let me call sampler. Okay, and then you give it to quantizer. Output of quantizer is given to encoder. So when we were discussing pulse code modulation system, that time I did not put this low pass filter, but anyway, make sure that this low pass filter must be there. Okay, and to make sure that there is no aliasing distortion. Okay, so you must make sure that your sampling rate and the low pass bandwidth are properly matched, otherwise high frequency component will pose as a low frequency component. As I said, typically for voice signals, this low pass filter will have a bandwidth of less than or equal to 4 kilohertz. Therefore your sampling will be done at the rate of, yes, sampling frequency will be done at the rate of 8 kilohertz at least. And after the sampler, followed by sampler is followed by the quantizer and the encoder. And this typically these two are realized as one block in general in practice. So the combination of quantizer and encoder both are realized as one block. Okay, and typically known by the name of analog to digital conversion. Analog to digital conversion, or A to D converter. Okay, that's it. So this quantization process and the encoding process are really slightly indistinguishable at the implementation level. Okay, so they go more or less hand by hand. And as I said, in speech signals we used typically 7 to 8 bits of quantization. 7 to 8 bits of quantization. So n is equal to 7 or 8. So what about the q? Q is equal to 2 to the 7 or 2 to the 8. That is 128 or 256 level of quantizations. So that means for each sample I need 7 bits or 8 bits to represent. Each sampled value is represented by using 8 bits. Let's say n is equal to 8. In this case, I am doing the sampling, right, at 8 kilohertz. Therefore, I have 8000 samples in a second, per second, and each sample is represented by using 8 bits. Therefore, 64 bits per second. Okay, your sampling rate is 8000 hertz, and each sample is being represented by 8 bits. So the final rate at which you have to transmit this data is 64 kilobits per second, kbps, and that's a standard PCM data rate. The 64 kbps is the standard PCM rate for voice signal. And now this 64 kbps is transmitted onto a channel which is usually noisy. Okay, the channel is usually noisy. It introduces some kind of noise. Okay, it introduces noise, and to take care of this noise at the receiver, you have to employ something called a matched filter. So we will discuss the operation of matched filter as we go along the course in detail. In fact, this diagram could be that of the receiver at the final destination, or even you can use it at the repeater also for for re-quantizing the signal and a retransmission. Not necessarily this going to be at the receiver alone. So the receiver diagram will be more or less the same. And after matched filter, you give it to D to A converter. And then again you put low pass filter to remove the high frequency component because of this sampling, and then you will get a M cap of T. So this part is receiver. Okay, you can use this part not only at the receiver, you can use at the repeater also. Repeater is a block which present between transmitter and the receiver. Now to take care of the noise, you use at the front end what is called a matched filter. We will talk about the need for a matched filter and its characteristics at a slightly later time in our course, not now. But broadly at this time, it is sufficient to appreciate that the main purpose is to be able to make correct decisions regarding whether in a particular bit interval a 1 or a 0 was transmitted or 1 or 0 has been received. Okay, and this decision is a non-trivial decision to make, because in the channel you are transmitting ones and zeros at a rate of 64 kilobits per second. So like 1 0 1 1 0 1 1 1 like this. If 0 comes like this, 1 comes positive pulse, and positive pulse, again positive pulse, then 0, then positive pulse, then again positive pulse, like this. So essentially you are transmitting sequence of pulses, and this pulse duration is fixed. Okay, this is my duration, bit duration. Each bit has its particular duration. Now because of the noise, this positive amplitude may appear as a zero amplitude or negative amplitude, and this 0 becomes, maybe due to noise, it looks like a 1. So there will be some error. Okay, so you may not be able to make correct decisions at the receiver whether in a particular bit interval, in this particular bit interval, whether a 1 or a 0 has been transmitted or received. Therefore the receiver operation is not trivial. Okay, so this decision is a non-trivial decision to make, because this pulses that is coming along with the lot of noise may be affected. So that is the reason we need to put up the matched filter. So it may not be obvious to determine whether 1 has been transmitted or 0 has been transmitted from the noisy signal, because the noisy signal is very weak to immediately see whether it contains a 1 or 0. The signal is already weak because it traveled through the channel, and the signal is affected by the channel noise, so it's kind of difficult to make a decision. Therefore, to be able to make a good decision, you do a certain kind of processing on the received signal, and this processing is known by the name of matched filtering. Therefore, the purpose of matched filtering is to remove the noise, okay, to get a sample value based on which you can make the decision more reliably, okay, depending on the output of this matched filter. Therefore, the matched filter is remove the noise as much as possible. And make decision more reliably, and it helps to make decision more reliably. Okay, but we will go into the details of the matched filter slightly later, and at the moment we just have to know that such a processing is required to take care of the noise in the PCM system. Once you have got that done, then you can take a decision whether a 1 or a 0 was transmitted, and then follow it up by with a D to A converter. Okay, these bits are collected and put into A to D to A converters, and that output is usually quantized version of the input signal, and therefore you low pass filtered it, and finally get your estimate of the transmitted signal. Okay, here M of t is a message signal, and at this point you will get M suffix S of t, that is sampled signal, and here at this point you get M suffix Q of t, that is quantized signal, okay. And output of the D to A converter is M cap of t, which is estimate of the quantized signal. And finally, after low pass filtering, again you get an estimate of the original signal M of t. Okay, now why do we need low pass filter? Because there could be still some noise that has trickled through, and more importantly, your quantizer simply introduces steps, a staircase kind of thing, which will be removed by low pass filter. Okay, the low pass filter smoothen it out whatever the error the quantizer has introduced, because the quantization noise has also a broad spectrum, so you remove as much of its energy as possible from the band of interest. Okay, as I said, this block diagram not only used at the receiver, but it is also used at the repeater also. Okay, and in case if you use this block at the repeater, then again you have to use sampler and quantizer and encoder, but usually at the repeater level one can just clean up the pulses and retransmit rather than carry out the process of D to A conversion and low pass filtering. Basically you have to still just retransmit it. Okay, so that's all about the pulse code modulation system. Now let us go into these things a little more in detail. Okay, this is periphery level simple block diagram. So input signal message m of t is given to low pass filter, so that it limits the frequency component up to 4 kilohertz, and after that it is given to sampler followed by quantizer and followed by encoder, and output of the encoder is given to the channel, and channel introduces noise. So this noise will be removed by the matched filter. That is why we kept this matched filter at the front end of the receiver, and then output of matched filter is given to D to A converter, and then you give it to low pass filter. Okay, now let us get into these things a little more detail. First let me draw the diagram. So we will see transmitter and the receiver in detail. So message signal m of t is given to low pass filter. Okay, and this is sample and hold circuit, because you should hold the sampled value for a certain time in order to convert into digital. Comparator and comparator output. Here you have ramp, generator, and the output of ramp generator is given to comparator. Here you have encode command, and then you have clock, binary converter, and then parallel to serial converter. That's it. And this is PCM output. This is called a code word, and this one is given to binary converter, and the clock is given to, it's not binary converter, counter I think. Okay, let me check. And the encode command is given to ramp generator, and the same clock is given to sample and hold circuit. Then here you give transmit command. That's it. So this is a block diagram of an A to D converter, which I am sure you can recognize. Okay. Now what kind of A to D converter is this? This is a ramp type. Okay. So there are many types. Okay, not necessary to use only ramp type. You can use many. So you have the message signal m of t, which is given to the low pass filter, followed by sample and hold circuit. So you have the sampled signal, and that sampled signal is held up. Okay, and the sampled signal is compared with the help of comparator. Just as this sample is being generated, you also give what is called an encode command to the ramp generator, which initiates the generation of ramp signal. It generates a ramp signal like this and comes down and generates a ramp signal like that. So this incoming sample is compared with the ramp ramp output. Okay, so this is the incoming signal, and this is the ramp output. Both are compared. Okay, and when the ramp signal value exceeds the sample value, the comparator generates a signal which becomes a stop signal for the binary counter. This is a counter. So the ramp is slowly increasing, right? At this time the counter starts to count. Okay, if it let me draw here. The operation goes like that. This is the time axis. This is the voltage. Let's say it increases 1 volt, 2 volt, 3 volts like that. Let me drop to 4 level. Now it increases in 1 second, it increases this much. I don't know, in one time unit, 1, 2, 3 like this. These are time units. Probably you might have studied this in your other course, okay, in electronic circuits. I don't know. Anyway, let me cover here also. Now in one time unit, if it is increases this much 1 volt, then by the time the binary counter is increased to 0, 1. It counts by 1 in one time or 1 clock period. Let's say it's proper to call 1 clock period. And in the 2 clock periods, the ramp generator generates ramp voltage up to this level. Okay, so in in 2 clock periods, your binary counter increases from 0, 1 to 1, 0. In case if the incoming signal level is 4 volts, let's say, so your ramp generator will keep on increases up to 4 volts. To reach the 4 volt, how many time unit do you need? 1, 2, 3, 4 time units. So this 4 will be represented by 1, 1. I'm sorry, let's say this is 0, 1, 2, 3 like this. So let's say 3 volt, because 0 to 3 I'm counting, okay, 4 levels. So therefore 1, 1. The moment you reach this voltage, then this voltage will be equal to the incoming signal. At that time, the comparator generates a stop signal, and that stop signal is given to binary counter. Okay. I think, am I drawing this correctly? Yes. Okay, so the incoming sample is compared with the ramp output, and when the ramp signal value exceeds the sample value, the comparator generates a signal which becomes a stop signal for the binary counter. That time the binary counter stops, so it stops at 1, 1, at this 1, 1. Okay, the binary counter is counting from 0 onwards. It starts from 0, 0, 0, 1, 1, 0, 1, 1 like that. And at that moment, this level is exceeded. The counter is made to stop counting. The binary counter is made to stop counting. And the output of the counter now represents this 1, 1 level. Okay, this level to which the ramp has reached, which also represents the level of the input signal. Okay, my input signal is 3 volts, and this 3 volt is represented by this point, and this point is equivalent to 1, 1. That 1, 1 is achieved through this binary counter, and therefore this 1, 1 becomes the binary representation of the sampled value. Okay, so this 1, 1 becomes a binary representation of a quantized signal, and this quantized signal, this binary representation is in parallel form. Okay, so we need to convert it into a serial form in order to transmit. Okay, that's the essential part. So you need to convert the parallel form into serial form in order to transmit the PCM output. Okay, so this is a difference between A to D converter and PCM systems. So normal A to D converter output is in parallel form because typically it is going to be used in a machine in which all the bits are required to be available simultaneously. But on a line, transmission line, you have to transmit these bits in a serial mode. So you essentially transmit, so the essential difference is that you need to have a parallel to serial converter for transmission onto a line. Now you can ask a question, what is the connection between sample and hold and binary counter? See, these are in the common line. Okay. The clock is being counted. Okay, you apply the clock and the clock is needed to count the clock is needed for the binary counter in order to count. So therefore the clock is being counted, and in that duration of time you need to hold the sample value. Okay, and sometimes people may feel that the ramp type A to D converter is slow. Little slow. Okay, now, well, it will depend on the rate at which you want to do things. Yeah, if it is a voice signal, this ramp type A to D converter is good enough. You can use it. But if it is a picture signal which you want to quantize it at a very fast rate, then maybe you require a very fast A to D converter. So in that situation, you may not use this ramp type A to D converter. You have a different kind of A to D converters. Okay, there are different kind of A to D converters which are available. So this is just an example. So this is not to say that all the time you are going to use this kind of A to D converter. See, technology has made available many different kinds of A to D converter, and we will choose the most appropriate ones, both from the point of view of cost, okay, as well as from the point of view of meeting your needs or affordability. Okay, so always it is a trade-off between cost and what you can live by. Okay, so you should always know trade-off, okay, between the cost and what you can live by. Now that's all about as far as the transmitter part is concerned. Now let us look at the receiver in detail. This is also pretty simple. So PCM input, and this PCM input is given to matched filter. Again, as I said, the front end of the receiver must be the matched filter in order to remove the noise, and this is given to serial to parallel converter, because here we had a parallel to serial converter, right? So the inverse operation is serial to converter, and then here you give it to synchronization. Let me draw this diagram first and then I will explain the operation of each block. And then here it's a resistor network. And then you combine everything, give it to amplifier, op amp, feedback path, then sample and hold, okay, and low pass filter, that's it. Okay, so you have the matched filter at the front end of the receiver, followed by serial to parallel converter, so which is essentially a resistor network, okay, resistor varying network, followed by an op amp. This is op amp, okay, operational amplifier. Now the important different thing here is this block synchronizer, okay, which I have not talked about so far. But the synchronizer is very crucial to any digital communication system. Okay, not only in PCM, whatever the digital communication that we are going to talk about in the future, synchronization is very, very important. And this in fact makes the digital communication receivers much more complex than corresponding analog communication receiver. Okay, because of the synchronization part, it makes the digital communication receivers much more complex. In fact, synchronization is there in analog communication also, for example in double sideband suppressed carrier modulation also. But that kind of synchronization is also needed here, we will see that later. Okay, but this synchronization is slightly different. This synchronization is slightly different from the synchronization that we used in analog communication. Okay, so the kind of synchronization we are referring to in analog communication is basically that of the carrier synchronization. In analog also we have synchronization, that is carrier synchronization, but in digital we have something different. Okay, so we need carrier synchronization here also in digital communication. Okay, but remember when we are when we were doing in the process of encoding, we were talking about sample. Okay, and the sample put them in a group of bits, and these bits were transmitted like 1 0 0 1 1 0 1 1 0 like this. Then how do you transmit? For 1 you transmitted a positive pulse, 0 means no pulse, and again 0, then 1 1, then 0 1, again 1, then 0, like that. So in this case you need to know where the pulse starts and where the pulse ends. Starting time and ending time of the pulse is needed. Okay, so each sample is represented by a group of bits. Suppose in case if I use 4-bit word, then at what point my word starts and at what point it ends. Okay, because you are transmitting, you are getting this sequence of pulses. So at the receiver you don't know where a particular word starts and where it ends. So you require a synchronization at the word level. So synchronization at the word level as well as bit level also. So why do we need the synchronization at the word level? This is needed in order to mark it different group of bits. In case if my word starts here, so 1 0 0 1, this is my word 1, and then 1 0 1 1, this is my word 2. In case by mistake if you make a wrong decision, if you take this as my word, then completely gone. 0011, right? So here 0011 is equivalent to 3. Here 1011 is 9. So instead of decoding as 9, now you are decoding as 3. And in this gap 1011, 1011 is 11, right? Code word 2 is 11 volts. But if you make some error, yeah, 0110, like this, 0110 is 6. So instead of 11 volts you are making 6 volt. Therefore accurately you need to know at what point the code word starts and at what point the word ends. Therefore, in order to achieve this kind of word level synchronization, we need the synchronization block. So because of that synchronization block, your digital communication receiver is complex than your analog communication receiver. Okay, so definitely you need synchronization at the word level in order to mark it different groups or bits from each other. And you also require synchronization at the level of bit level, as said, word level and also bit level. Okay, so you need to know, this is important point, you need to know where each bit starts and where each bit ends. Okay, so this information is needed in order to enable the matched filter to do its job properly, not only for grouping the words or decoding the words. The matched filter also needs accurate bit duration, otherwise the matched filter will not do its job properly. Anyway, we will see that matched filter operation at a later stage. Okay, the matched filter has to remove the noise for a particular pulse. So the matched filter works on pulse by pulse. It takes the first pulse and remove the noise. Take the second pulse, remove the noise. Take the third pulse, remove the noise. Take the fourth pulse and remove the noise. Therefore, the matched filter has to be informed that the pulse duration, at what point the pulse starts and at what point the pulse ends, in order to do its job properly. Okay, so in order to enable to make a correct decision whether in that bit interval a 1 or a 0 was transmitted, to be able to make the decision correctly for that interval, it must know, the matched filter must know where the interval starts and where it ends. So the matched filter requires such information. So synchronization is not only needed to make the correct decision for every word, it also needed to identify the starting point and ending point of each bit, and this information is very important for the matched filter. Okay, so the matched filter needs to know where the interval starts, where the bit starts and where it ends. Okay, therefore if you have a good bit level synchronization, it is very easy to derive the corresponding word level synchronization. If you know the bit level synchronization, then you know how many bit is needed for a word. Okay, for example, if you take 4-bit word, then you just count 4 bits and then you can say, okay, this is my first word and this is my second word. So it's not a big deal. Okay, so whenever you have a good bit level synchronization, it is very easy to derive the corresponding word level synchronization. Leads to word level synchronization, because we know how many bits the word contains. Okay, but you may still require to know precisely where the boundaries are. Okay, at what point this guy starts and what point this guy ends, what point it starts and at what point it ends. So for which one has to do additional things which are slightly irrelevant to the basic job of communicating information, but anyway we need to do that. Okay, for example, you may like to transmit some kind of preamble. Okay, that and all, okay, slightly related to your data communication or computer communication, but generally we will not transmit the information straight away. So we will transmit some preamble for that synchronization, because you will ask the receiver to get ready. Simply you will not transmit, and you cannot expect the receiver to do the receiving operation. First we have to initiate the receiver and tell the receiver, okay, see, I'm going to transmit some information, be ready, and this is my starting point and this is my clock duration, and all the information you have to send before you transmit your data. Okay, so you have to make a connection between the transmitter and the receiver, and then you start to transmit. So some protocols have to be involved, so that your receiver has to set up to receive the information when it is started or when it is transmitted. So there are various kinds of protocols. Okay, so we will talk about them at an appropriate time if time permits. Okay, so when I say preamble, it is some kind of protocol. This preamble is done at the beginning of the transmission. Similarly, at the end of the transmission also, we will send some information to inform the receiver that I have completed, I have transmitted all the information. So synchronization is over. So we will stop the connection like that. Okay, so at the moment we are only looking at the block level description of your PCM system. So we will be going into the details of many of these things later, because they will be required in many other contexts, okay, rather than just PCM context. Okay, so that's all about the pulse code modulation system level implementation. Thank you very much.